Good morning, everyone. Today we are going to see theory of simple bending. A small introduction to the terms we are going to use in the formulas. So myself, S.K. Karthikeyan, Associate Professor, Department of Mechanical Engineering, Kongunadu College of Engineering and Technology. Now coming to the introduction, the theory of simple bending. It is nothing but a pure bending. We are going to considering only a bending only. So when a portion of beam is free from shear force and is subjected to only bending, that is said to be pure bending or simple bending. So in that we have some assumptions. The assumptions are a consideration that we are going to perform doing the calculation. So here we have some list of things. You see, a beam material is homogeneous and isotropic. So isotropic means same elastic properties in all directions. That is the exact meaning of using an isotropic word in this consideration. Then beam having uniform cross section throughout its length. That is one of the consideration. Then the beam is stressed within the elastic limit. Then the Young's modulus is same in both tension and compression. Then the next one is the loads are applied before bending. Then stress concentrations are neglected. Then radius of curvature of bending is very large as compared to cross-sectional dimensions. Apart from bending, all other deformations are neglected. Then the last point is there is no resultant thrust on the cross section of the beam. So this is the bending equation. You see m by I equal to sigma by y equal to E by R. The terms are m is nothing but bending moment, I is the moment of inertia on the axis of bending, sigma is the stress, and y is the distance from the neutral axis to the extreme end of the material, and E is the Young's modulus, and R is the radius of curvature of the beam that is going to be bent. So now we are going to see some terms, that is moment of inertia and section modulus used in the formula. Suppose you are treating the beam as a rectangular one. So what is the formula for that? So that is, I have shown it in the figure. You see the cross section having the values B and D, and it has a D by 2, that is the distance from the neutral axis to the extreme edge of the arrangement. So D by 2 is the value calculated from the neutral axis. So coming to the moment of inertia formula, this is I equal to BD cube by 12. So the next one is distance of outermost layer from the neutral axis, NA is Y max, that is D by 2. So coming to calculation of section modulus, Z equal to I by Y, that is Y max. So you substitute all the values, BD cube by 12 divided by D by 2. Finally you got BD squared by 6. So this is the section modulus value for a rectangular section. Next, coming to the next one, hollow rectangular section. You see the diagram having two portions. The inner one is mentioned in the small letter BD. The outer one is mentioned in the capital letter, capital B, capital D, and capital D by 2 is the distance from the neutral axis to the outermost fiber. So as usual, you find the bending moment. There is a moment of inertia, that is I equal to capital BD cube by 12 minus small BD cube by 12. So finally you take the LCM and you get BD cube minus BD cube divided by 12. Then as usual, Y max equal to capital D by 2. Substitute the two equation in the section modulus equation, that is Z equal to I by Y max. So finally you got I divided by 1 divided by 6D BD cube minus BD cube is the final answer. Next, the next one is we going to consider circular section. The bending moment, that is the moment of inertia for the circular section is pi by 64 d power 4, and y formula is d by 2. So as usual, substitute I and y values in the section modulus equations. That is pi by 64 d power 4 divided by d by 2. Finally you got pi by 32 d cube is the section modulus for a circular section. Then coming to next one, hollow circular section. Moment of inertia is pi by 64 capital D power 4 minus small d power 4. You see the thing in the diagram, There are two circles. The outer one is capital D, inner one is small d. The distance is d by 2, capital D by 2. That is from the center neutral axis to the outermost fiber. That is mentioned as y max as d by 2. Then as usual, section modulus I by y is the formula. So you substitute all the thing, you finally get pi by 32 into d power 4 minus d power 4. So that's all. Thank you all.